Like I can hit some of this one.
But if this is get extra challenge, I mean, all has all chance of everything. It just it matters if you focus on.
Who's this guy?
What do you want here? Why don't you red? It's Cowboys. Oh, you something.
Right?
Yeah.
Look at him see that. I'm very that was the first week about sports. Well, actually, some of those seasons. I didn't realize that they actually had kids. So, and so that's why I think that
I didn't understand the concept of like we American hit the stats and stuff. Like American Career, I think now is the record.
Yeah.
And there is better. I'm like, what? Look at that good. Right? What? There were some. It's like about 40 is never in the stats. At least that's what I've been told. Now, whether it's true or not, that's a different story. It's been a long time. Although I took my character and I married off Anna, and I don't think things are. I'm running with overpowered. So this is
Yeah, I'll start at Steve Stones.
Okay, so I have uploaded an example review. So what we'll do is we won't have the review due today. We'll just push all the reviews and scribes by one class. So Thursday we'll start. Let's discuss how you should write the review. and then we can start doing that. So the rule that we used last time was that if a paper I'm discussing on Thursday, you should send me the paper by Tuesday, right? And you should read the paper and start writing the review. Now on Thursday, whatever discussion we do in the class, you incorporate that in your review and submit by Thursday midnight, right? Then the scribe takes over, right? The scribe is not due on Thursday midnight. Scribe will take the paper, take the review and comment on the review, right? So now we will see a format of the review. So scribe will be due on, so Thursday is done, so Friday, Saturday midnight, so 2 days, right? So if the paper is due on Tuesday, then scribe is due on Thursday. So if we are discussing the paper on Tuesday, you should send me at least the paper on Sunday, and then you keep on writing the review. On Tuesday, based on discussion, you update the review and submit by Tuesday midnight. Then the scribe submits the scribe by Thursday midnight. Right? Yes.
Okay. Do you want all groups to submit paper Thursday?
All what?
What are we supposed to submit for this Thursday?
So today group 1 and group 2 had their paper due, right? They sent me a paper. So if the paper is due on Tuesday, like we are discussing the paper on Tuesday, then you should send me the paper on Sunday midnight. So if group 3 and 4 are reading one paper, then you should collaborate, you should talk to each other and find out the paper, send me by Sunday. Now if the paper is due to be discussed on Thursday, you send me by Tuesday midnight. And just give me 1 day to read it. So now what happens is that the paper that we discuss on Thursday, let's say this coming Thursday we'll discuss a paper, and that's the paper of group 1 and group 2. So group 1 submits the review by Thursday midnight. Okay? Group 2 takes that review as well as the paper and summarizes what we have discussed in class. Right? Summarizes what we have discussed in class and sends out the scribe by Saturday midnight. Now if a paper is due to be discussed on Tuesday, you send me the paper by Sunday midnight, write the review, submit it by Tuesday midnight, and the scribe takes that review and whatever things we discussed in class and submits the summary by Thursday midnight. Okay? So that's how we'll do it. Now the first one I'm shifting one because we didn't discuss the format of the review, we didn't discuss what you need to write. So let's shift by 1 week, one class, not 1 week. So we're shifting by 1 week. So group 1 and group 2 will start on Thursday, group 3 and group 4 will be on Tuesday and so on. Okay. So your team will update the schedule accordingly. Okay, now let's talk about this. So Ecotag was the paper that we were discussing last time. We didn't really discuss the technique, how it does ecotagging. So let's first discuss the technique so that we understand the paper, and then we will see how the review is going to be written and how the scribe is going to be written. Right? So let's talk about this paper. So we said that there are many different ways of doing window localization. Wi-Fi is one, taking FM radio frequency, that is another one, and this is one more modality that you can take, taking the sound signatures, right? So if you look at this figure shows you how or what is the sound signature. So this is the received attenuation of a flat frequency sweep So what they did was they sent out a monotonic signal, right? And it has only one frequency. It's very difficult to create a signal with just one frequency. But what you have is a signal that has one peak in the fast Fourier transform. That you can do. So you take a signal, do a fast Fourier transform, it will have one big peak, and the other peaks will be attenuated, but there will be other peaks. So you take such kind of a signal and you send it in one direction. So what will you get? So this is frequency response of what you get, the reflection. Frequency response means you get some sound that is reflected from some surface, and then you do a Fourier transform of that sound that you get reflected from the surface. So you see there are two peaks. So they say that okay, this is over 100 different trials. And over 1 minute they sent, and 100 times they did that, and then they did an average. Right? So that's why that red one is the mean, and the blue one, I think, blue one is the 5th percentile, black one is the 95th percentile. Right? Then however many times you get those type of signature. So you see there are two peaks typically. Now you don't really get two peaks, you get multiple peaks. Right? You get infinite number of peaks with reducing amplitudes. Why do you get that? So imagine that you have some objects which are very close by. Right? So the first peak that you get is basically the feedback from the mic itself. So you have a smartphone, you are using the mic of the microphone of the smartphone to send out a signal, and then you are using the headset of the smartphone or the first you use the speaker to send out some signal, and then use the microphone of the smartphone to sense what is being reflected. So the first peak occurs right at the time when you send out the signal. So what is that peak? That peak is basically whatever you're sending, you are also sensing that. Now then you get a second peak, which is reflected from nearby objects. So objects that are nearby, they reflect your sound signals and you sense those. So that is your second peak. Now you also get a third, fourth, fifth peak. Why? Because there are some objects that are further away and they reflect those signals. So those signals come at a later time. So if you look at the time frequency diagram, let's look at the time frequency diagram. This is the time frequency diagram. So this is what you get at the microphone. So here what they are doing, they are just sending one signal, one sound signal, and trying to listen to the reflections. So this is what you get from the microphone. So you see that there is one peak that is right at time 0. So this is the peak that is not related to any reflection, but whatever you are sending, you are sensing it back. Right? But then there are subsequent reflections, and you see that all the reflections are attenuated. Right? So this reflection is from objects which are nearby, saying 1.5 meters away. These ones are from objects that are a little bit further. So this is they are saying that this is a unique signature of a particular location. So if you can take this signature and put it inside a machine learning algorithm, then based on this signature you can identify locations. Now it turns out that not only locations, it also depends on the orientation of the smartphone. That's why you need to place the smartphone in the same orientation as you placed during training. So when you place the smartphone, you draw a box. Right? And next time you place the smartphone, you place that exact same orientation. So that is the basic idea. Now there are problems. So the first problem that they are saying is that you cannot really, so ideally what you want to do is you need to use this sound frequency that is not in the hearable range or audible range. If it is in the audible range, it's annoying, right? Every time you want to do something with your smartphone, you keep it and starts shouting. That's not good. So you have to take frequencies that are not in the audible range. So if they are not in the audible range, then that means either they are too big, too high frequency, or too low frequency. Right? Now the problem is that the microphone that you are using to sense, so you send one using the speakers and then you sense also, right? That every microphone has a matching filter. And matching filter is what? Because this microphone is only capable of recognizing voice, right? So it has a matching filter. Matching filter means it rejects everything that is less than 20 hertz and it rejects everything that is more than 20 kilohertz. There is a band pass filter. Right? So this is the range, audible frequency range. Right? So that since it is a matching filter, so if you use higher frequency, it will have more attenuation. So you won't. So that signature, you won't get a very good signature or very sharp signature. You'll get something which is blurred out because the attenuation in that range will be very high. So that's why they are saying that okay, you need to use sound signals in the audible range. Now, so this is a sign of a good paper. That is a drawback, right? If you have sound signal in the audible range, that is a big drawback. Because every time you draw a circle around it, it will start making noise. So they did a user survey saying that whether this noise is annoying or not. And they said that okay, we did 40 users and everybody said it's not annoying. So then it's not annoying, it's good. So that is a sign of a good paper, that you found a drawback and you have to reason about why that drawback is not affecting the usability of your system. So all these things, when you are doing reviews, all these things you need to take care of. You need to see whether they have addressed possible potential problems or not. Okay? So that is one problem. The other problem they are saying is that you should not just send one signal and be done with it. Why? Because of this property. This is what they are saying that if you look at figure 9, right? Figure 9 says that okay, they are saying that you should always send sound signals at a given frequency. Right? So which means that you just don't send one signal. You keep on sending that signal and keep on receiving the reflections. So maybe do it 100 times or 200 times. Just don't send one signal. Why? Because they are saying that if you find out the time frequency response of the reflection on the two microphones, so right hand side microphone, left hand side microphone. So you found out the images, not images, you found out the reflections and then you did a time frequency analysis. What is it? DWT. Right? Do discrete wavelength transform of the sound signal that you receive. Now if you plot it there, then what they are saying is that if you just send one sample, just one shot, then you have this kind of a time frequency response. If you send two shots at one sample delay, then you have this. If you send 3 shots or more shots at 2 samples delay, then you have this. Now what is the difference between these 3 figures? You see that this white band is becoming sharper and sharper. Right? 0 sample delay, this white band was spread across the entire time frequency domain. 1 sample delay, it became more sharp. 2 samples delay, it became even more sharp. Right? So they are saying that as you increase the delay and you increase the number of times you are sending this sound frequency and you receive all the reflections, if you do a DWT of all those reflections, the white portion becomes sharper. Now if the white portion becomes sharper, what will happen? You will have a sharper signature. Right? Sharper signature means the distance between 2 different types of signature will increase. it will become easier to cluster, easier to classify. And so if you are using a support vector machine or some machine learning system, then it will be more accurate. Now, what is the drawback of having sharper images? It means that you have to send signals which are far apart in time. So you will take more time. You will take more time to match or to detect the location. Right? So it is a trade-off between accuracy of classification and time taken to do the classification. So they do a very good analysis of that. So that is also a very important contribution of this paper. That instead of sending just one signal, you send it at a frequency. You keep on sending. So that's why they are saying that this should be the way that you should send. You should not send just one sound signal and stop. Right? You should send sound signals at a regular interval and then look at the images. So these are some of the things, and then they also talk about how what happens when you control the volume. So they are saying that you should have 100%. 100% volume is not good. 1% volume is also not good. There has to be somewhere in between, right? So 100% volume, why not good? Because again, it depends upon the matching filter of the microphone, right? If you look at the amplitude response of the microphone, then larger amplitudes tends to be dampened more. So if you might have done this experiment, if you have a mic and you shout at the mic, right, it starts crackling. So that is a poor frequency response of the mic. Also, if you have very low volume, then also you cannot hear clearly. So again, a microphone also has a very specific volume range within which it is good. Right? It picks up sharp voice. So that is the effect that they also found out. Now so all these are good things to write about this paper. Now one bad thing to write about this paper is that they didn't really test on changing scenarios, but they kind of glossed over it. So the scenario is, what if I have I put my smartphone in the kitchen. I took the sound signature of the kitchen. Next day I had this big trash can made of tin, right? And I removed that trash can. Now tin is a good reflector of sound. So the time I took the signature, I had that big tin trash can, and it reflected the sound. You got a very sharp sound. But the next day I removed that trash can. I will get a very different reflection, right? Because that big trash can is not there. So they didn't really evaluate those scenarios. Like, what if the objects that are there are good reflectors, and then you remove those good reflectors. So material of the objects that are nearby, they don't do an analysis on that. So that is a negative point. And they talk about this, that okay, if you have larger objects and you move them, then that might be a problem. But they never talk about the material of which this object is made of. And what if I move a large object that was made of plastic versus a large object that was made of tin or steel? They don't talk about that. So those are kind of drawbacks. So now whenever you write reviews, how to write reviews? So I have uploaded a sample review of this paper, Ecotype. So there are 3 sections, or actually 4 sections that you need to write. First of all, you need to write a summary. Now I capped the page limit on reviews to 2 pages. You should not write more than that, because it becomes a problem for me to read. So there are 4 sections. Summary means you summarize the paper. What is the paper about? What is the main contribution? That is what you do. Now, while you are writing the summary, you should also talk about or you say that, okay, this contribution might be good mathematically, but is it useful? Is it practical? What will happen if I don't have that paper? If I didn't have this paper, what would I miss? Right? So you have to write that in the summary. So first of all, what is that paper about? Then is it applicable to this class? Third is whether this paper solves a very important problem or not. How important is the problem? The paper might have some complex things, but it solves a problem that is not important, right? So how important is that problem? And then fourth is what will I miss if I do not have this paper? What won't I be able to do, right? Or rather, if this paper enables something that I couldn't do before, what is that thing? So that is what goes in summary. Then you talk about the positives. You can write bullet points here. Right? In bullet points, you write about the positives of the paper. And you don't have to praise the authors. You don't have to say, oh, they are so good and so bad. Right? You don't have to say those things, but you evaluate the paper. You don't say that the authors are from UC Berkeley. That's a positive point. No, not like those. You talk about the paper. And then you talk about the negatives. Now, while you are talking about the negatives, don't say that those authors were stupid. That is not a negative that I want. Constructive criticism. Don't abuse the authors. And also, when you are writing positives, don't think that you wrote the paper. Often I saw some reviews that we did this, we did that. You didn't do this. The authors did it. Right? So when you are writing positives, don't assume that you wrote the paper. And when you are writing negatives, don't assume that your friend wrote the paper. Right? So be constructive criticism is for the negatives, and positives, what is really useful. And then what did the authors do to cover up their tracks? So every paper, every technology that has been proposed will have certain pitfalls. So those pitfalls have to be exposed, and those pitfalls have to be taken care of. If the authors don't take care of those pitfalls, then those are negatives. And if the authors talk about those pitfalls and say how do they address them, then those are positives. Right? So you take a look at this review. This is an example, good review. These groups have done. This is an example review. Take a look at this, and you can get a better idea. Now the fourth one is future use. Future use means, okay, you have this echo tag. Now it is being used to just solve this Indo-localization problem, right? But the technology can be used elsewhere as well. Sound-based signature. Where can I use it? For example, a long time back, maybe 4 or 5 years back, we had a project where we did security using sound signatures. So we said that if two sensors have the same sound signature, then maybe they are close together. For example, they are on the same human body. Maybe. Right? So based on sound signature, we can identify proximity of sensors. So if the sound signature matched, then I say that this sensor is very close to this. Now if this sensor wants to send me some data, then I can accept that, okay, this is close to me, so maybe this is a part of my network. But if some remote sensor sends some data to this particular sensor, there will be sound mismatch. So then I can say that no, this sensor is remote. So that means somebody is trying to control me remotely. So let's not give him access, or give that sensor access. Okay? So you can do proximity-based access control based on sound signature. So that is one place where you can use this. Right? Security is one place that you can use this. So think about where else can you use this, and write about those. Right? Those are future uses. So that is the purpose of a reviewer. Now what is the purpose of a scribe? Did I upload that? No, I did not. Let me upload a scribe. So this is a scribe. Now a scribe has again 4 parts. So basically, in summary, what the scribe should do is it should comment on the comprehensiveness of the reviews that the reviewer has given, and also summarize the discussions in the class. And because the reviewer, the group that is doing the review, doesn't have a fair chance to write about the class discussions, right? So that is the purpose of a scribe. Has to summarize the class discussions. So now, while the scribe is summarizing class discussions, it has to divide everything into again 4 categories. First category is technical completion of the summary that the reviewer has written. So you have to read the review and you have to see whether whatever the reviewer has written is a technically complete representation of what the paper talks about. Right? So that will be influenced by what we discuss in class. There might be some things that we have discussed in class which is not there in the review. Right? So technical completeness involves that. Was there something that we discussed in the class and it was not there in the review? Right? Then you discuss the pros and cons of the something else. Hurricane Irma? I keep watching live updates. Now I can't, so I don't have anything to do. So pros and cons. What are pros and cons? So these are not pros and cons of the paper, but the pros and cons of the review that the reviewer has done. So the reviewer might have highlighted something as a very good positive, but the scribe thinks that no, this is not really a good positive. People have already done this, or this is not really novel. So you talk about those in cons. So cons means it's not very good, whatever the reviewer has said. So if the reviewer says something that is very good, and nobody has done that, these authors do that, and you find 10 papers doing the same thing, then you talk about that. That is not really right, whatever the reviewer has said. But pros, what you can do is you can talk about the accuracy of the review, right? Whether the review is comprehensive or not. So those kind of pros. So you can get an idea about what the pros and cons should be by looking at this scribe. Right? Then the thing is feasibility and importance. So that is a very important section. So you have to talk about, so Ecotag, they have proposed that, right? Now, how feasible it is. Feasibility means, can you deploy it in practice? Right? Many times the papers don't discuss that, and we will discuss that in the class. That is the main thing that we will do when we talk about papers. The feasibility and the importance. Importance means, so first part is feasibility, whether we can implement it in practice or not. The second part is, if we have implemented it in practice, what will be the good thing about it, right? So all those things you have to discuss in the last section. So that is the purpose of scribe. Right? So I will upload this. I didn't upload this yet. Let me just upload it right now. And from next time we will talk about this. Now the paper that I got from group 1 and 2 is very good paper. So what I will do is I will upload that paper today. Actually, John, they sent to you also. Can I upload that paper? So what we can do is, if you are interested, then you can read that paper. Otherwise, anyways, we will discuss that paper in class. That paper is called Care Droid or something, right? You submitted that paper? Care Droid? Yeah. So that is very relevant to the topic that we are discussing of adaptation, right? So they are saying that they are developing a middleware that can facilitate adaptation in mobile computing applications. So we'll talk about that paper when we talk about it. So next class. and you can write the review and then the strike. Right? So any questions regarding this? Okay. So then let's go and start a discussion on the implementation side of things. So last time with respect to implementation, we finished activities, we did services, we did broadcasts, right? Now we come to a very important topic, multi-threading in Android. So let's talk about multi-threading. So I like to use this presentation. He has done a very good presentation on multi-threading. So I'll use this. Now, before we go into this, we need to clarify certain operating system concepts. Did we talk about the difference between operating systems of Android, or not Android specifically, but smartphones, desktops and sensors? Did we contrast? No, we did not talk about that. So what is the mechanism of the operating system of a laptop? What do you do? Like how do you execute programs? I think we discussed that, sequential execution of programs, right? Whenever the CPU is idle, it's doing no ops, and then if you want to run a program, you have an interrupt and you execute that function, right? So that we said that any time the laptop never sleeps or the CPU never sleeps, it keeps on executing, no ops. But on the other hand, the sensors always sleep. They always sleep, and whenever there is something interesting event, they wake up and execute, and then go back to sleep. And so these are two different ways of execution. And then what happens in smartphone is kind of a middle way, right? So you have that CPU type execution where you don't really sleep, you always do no ops. But you also have this sensor type of execution where you have constantly listening for new events. And whenever new events occur, you call the listener, right? I think we discussed this. Now, given that this is the way that the operating system of smartphones work, we need to understand some basic concepts before we move forward with threads. So the basic concept is what is the difference between processes and threads? That also we discussed. And so what is the difference? What data? Which data? No, we are not getting specific. We specifically say something, right? So whenever you want to run a particular program, you need to give it memory. You need to give memory to 4 things: code, data, stack and heap, right? Now if you have processes, 2 processes are running and you are executing these 2 processes, then 2 processes coming out from a single parent process, they don't share anything. They have the same copy of code, data, stack and heap, but in a different memory location. But if you are considering about threads, like one process starts multiple threads, then they have the same copy of code, data, stack and heap. Not only that, they share the code, data and heap locations, but they have their private stack. That stack is different in a different location. So we share code, we share data and we share the heap. So that is thread, right? So now if we think about Android, then activity is a thread, services, they are also a thread, right? And what we'll talk about here is how the threads are getting created, and how, in code, how can you create threads and how can you execute them, right? But there are certain important theoretical things that we need to understand to understand the behavior of applications, right? How applications are executed in smartphones. So let's talk about that. So threads are what? Thread is a concurrent unit of execution. What is concurrent? What do you mean by concurrent? Anybody? What is concurrent execution? No. There is a difference between concurrent execution and parallel execution. This you should, you will know if you take operating system class. Right? What is the difference between parallel execution and concurrent execution?
Concurrent gives you the illusion that all the threads running at the same time, but they're scheduled in such a manner that it's actually the interchange.
So what is coming in? What is parallel?
So concurrence, it gives you the illusion of parallelism that each thread is running on a separate operating system, but it's actually running on the same operating system.
No, not separate operating system. Yeah, I kind of get what you are trying to say. So it is a part of the same operating system, it's not different operating system. So what she is saying is that parallel execution means you have multiple resources. Right, resources, let's say you have 2, 3 cores or 4 cores, and you are running 4 threads. Each of those are on separate cores, so they are executing with separate resources. But concurrency means you have a single core, but you are running multiple threads, but they are time sharing. Right? So they are time sharing in such a way that it gives the illusion that all these 4 threads are running at the same time. But actually they are not. They are time switching and very fast. They are time switching very fast. Right? So concurrent unit of execution means it can be parallel, but in general it is concurrent, which means these threads can execute on the same resource, but they have to time share. Right? So time sharing is concurrent, and parallel means your resource share. Right? We have multiple resources and you are operating. Parallel means you are actually executing at the same time. You are not time sharing. But concurrence means you are time sharing. You are not actually executing at the same time. So then continuing, a thread has its own call stack for methods being invoked. There are arguments and local variables. So stack is private, right? But code, data and heap, they are all shared. Now we come to the specifics of Android. Right? So what they are saying is each virtual machine instance has at least one main thread running. Okay, now let's draw a picture. And that picture is already also there later, I think. Yes, here. Right? Let's take this picture. So this shows the status of threads of different applications. So whenever we know that how the Android framework works, we cannot call it operating system. But Android framework, how it works is that whenever you start an application, you have to create a virtual machine, right? So now we make the distinction between processes and threads. So what are processes? Processes, you can consider that these are applications. So one application is one process. Now every process gets its own virtual machine. Virtual machine means what? At the very basic, virtual machines means it's an isolation of the memory. So you have an entire memory, RAM, let's say 4 GB, and you have decided that 10 applications get 4 divided by 10, that much memory. A very crude division. So every application gets the same amount of memory, and it has a virtual machine associated with that particular application. So now we will say that application means one process, right? So running an application means you have started a process in the operating system, and every process gets its own virtual machine. Now these processes can create their own threads. Each process can have multiple threads, right? So all these threads, they share the memory. Memory means what? How do they share the memory? So they have the same code space, they have the same data space, they have the same heap space, but their own stacks have different memory locations in that same common shared memory, right? So which means that if you have two processes, process P1 and P2, and you have process P1 has so many threads, right, 3 threads, and process 2 has only 1 thread. So these 3 threads will have somewhere, this is code somewhere, and they will share this memory location for code. Somewhere here there is data, they will share this data location. And let's say this whole part is heap, they will share this heap. But the remaining portion will be divided into 3 parts, each part representing the stack of that particular thread. So if we redraw this figure, let's redraw this figure with the explanation that we use. So if we redraw this figure, then what is happening? That there are processes P1 and P2, each having the same amount of memory, and each having a VM to themselves. So VM1, VM2. So there is application sandboxing, which means a thread in here cannot communicate with another thread in the VM2, unless you have declared a content provider. That we will talk about later. So there is a common memory resource, right? So this is a common resource, memory, and both have the same amount. So this is a common memory resource. Now this process has 3 threads, right? Thread T1, thread T2, and there is a main thread. Main thread can be activity thread if it's a UI element, or it can be a service thread if it's not an UI element. And this one has just one main thread, right? Now what I was going to say is that this memory can be divided into code. So let's say this is code, this is global data, right? And let's say this much is heap, right? So C for code, D for global data, and H for heap. So all these are shared. Shared means if I take a pointer P that and I do malloc, and in Java you don't really do malloc, but let's say imagine that, or you basically do new, right? And then you use dynamic memory allocation that way. But if you imagine that this code is written in C, the C is easier to imagine with respect to heap allocation. So if you have a pointer P and you have malloc, then it goes to that heap, right? And then every thread can access that P, and that P will be the same P that is in that heap, right? Now for the local variables and function arguments, each thread has its own stack, and each thread will have its own stack. Now where will this stack go? If there are 3 threads, then there will be 3 memory locations, or 3 ranges of memory locations. So this is stack of 1, this stack of 2, this stack of 3. So all these are stacks. If you have 10 threads, then you have 10 stacks, right? So they have their own stack memory and they have to share, as opposed to that main thread. So this main thread has, let's say this is code, this is data, and let's say this is heap. This entire thing is stack of a single thread. Now what do you do with stack? You keep the local variables, you keep function calls. What happens when you do not have more stack space? Right? No, stack overflow, you have to stop stack overflow. You don't really do stack overflow, right? You execute what? You stack, not caching. You don't really cache, and cache is different issue, right? To make it faster. Yes, so you have to, what you have to do, you have to take that, put it in hard disk. Right? You have to make more space for stack, for some other thread. Right? So which means that if you have lesser stack space, then your threads will run slower. It will start running slower. So now this is a unique, not unique, this is a property of, or this is a side effect of having virtual machines for processes. So what is the side effect? The side effect is that two processes, one process has many threads, the other process has a single thread. The process with many threads, for that the stack area is reducing. Right? So why do you have more threads? Why do you need more threads? What is the purpose of having more threads? Yeah, to increase performance, to do things in parallel. Right? While you are interacting with UI, you are also downloading something. Right? To do things at the same time. But what is happening is that in the process, since we have this VM type of assignment, in the process, each thread is getting slower. So the more the number of threads, the slower you get. Right? Because your stack size reduces. And if your stack size reduces, if you need more stack space, you have to throw some, get rid of some threads. Now get rid means you put the memory image into hard disk. You free up the stack memory space, do whatever you want to do in that memory space, and then once you are done, you take that memory image of the other thread, put it back. Right?
Android have the concept of disk cache,
Disk caching?
like moving to the disk and again like reading.
Yes, it can have, but it does not really do it in the, it does not use the SD card or anything like that, but it has secondary disks where it can put threads if they are not executing. It's not a property of Android though, it's a property of the Linux operating system that is underneath. Android as a framework is not worried about this actually. Android framework does not care about how much stack size is for each thread. It only cares about APIs. The Linux operating system does this. Right? So this is an operating system concept, not the concept of Android. Now the thing is, so based on how much memory you give to a thread, your thread will execute faster or slower. Right? Now the thing is, if you have too many threads and the thread is executing slower, to maintain user experience, again that is the main thing that we are after. Right? To maintain user experience, what the Linux operating system does for Android. So now this Android framework also influences the Linux operating system in some way. So how does the Android framework influence the Linux operating system? It puts a bound on the response time of threads. If the thread response time takes more than 3 seconds, it tells the operating system that you should kill it. But regardless of whether it needs more memory or it needs more time, you should kill it. If no thread should take more than 3 seconds to respond. Right? Now note that this does not mean that the execution time of the thread cannot be more than 3 seconds. Execution time of the thread can be more than 3 seconds. But it has to give a response. Response means it has to update something in the activity, main activity thread, and let the user know. Right? So in order to update something in the main activity thread, what it has to have some result. It has to execute something and give some result. Right? In order to execute something and get some result, it has to execute some functions. It has to update some local variables. So that means it has to manipulate the stack. Right? So this means that you have to manage the memory for every thread in such a way that no thread takes more than 3 seconds to respond. Right? So you have to do some sort of scheduling, a way to schedule things. Now this Linux operating system does this. It's not a new thing. CPU scheduling or thread scheduling is a very old concept of the Linux operating system. Typically it is first come first serve. Whichever threads comes in first, it gets the memory, right? And it executes. But this new metric of response time, which means, or which ultimately ends up being a user experience metric. This new metric calls for new types of scheduling policies. So Android uses something called completely fair scheduler, CFS. Okay? Completely fair scheduler. So we'll talk about that scheduler. So what does it do? Now this memory requirement of the stack can be measured using a single metric. We can talk about memory bandwidth. Memory bandwidth means what? Oh, this is memory bandwidth. Or we won't call it really memory bandwidth, we can also call it as thread bandwidth. And instead of memory bandwidth, we call it as thread bandwidth, because memory bandwidth has a different notion. Yes. No, that's what I'm saying, it's not the execution time. Thread doesn't have to finish executing in 3 seconds. It means that the response time has to be 3 seconds, which means that the thread has to respond, means come up with some output. It doesn't have to be the final output, but it has to come up with some output and show it in the activity thread. Right? So it doesn't have to be the final output that the thread has finished executing and it exited. The thread can continue running, but it has to update. It has to give some updates.
You can just say that I am alive.
Yes, you can just say that I am alive. But even in order to do so, you need stack. Any operation will need stack. Right? So you have to have some way of allocating that memory. So that is the way the completely fair scheduler. That's how it works. Now, how to quantify this memory allocation or stack memory allocation? How do we quantify it? So one way of quantifying is talking about thread bandwidth. So thread bandwidth is an indirect way of talking about stack allocation. So what is it? This says that this is okay. So in 1 second. So this is in 1 second, how much data can a thread consume? Now this is a very weird metric. What do you mean by how much data a thread can consume? So you think about the thread, it has some functions, right? It does some operations. And once it does some operations, it gives an output after doing that operation. How fast can it give an output? So if a thread takes 20 KB of data and gives an output in 3 seconds, an average metric can be 20 divided by 3. You can say that, okay, every second the thread takes around 6 KB of data. Yeah. So that is the thread bandwidth. You can talk about thread bandwidth like that. Do you understand this concept? This is a very different concept from allocating memory, right? It's a very different concept. But this has direct effect in allocation of memory. this metric, this thread bandwidth metric has direct effect, or rather allocation of memory has direct effect on this bandwidth. If you allocate some bandwidth, or if you allocate some memory, some stack memory, if you allocate more stack memory, the bandwidth will increase. If you allocate lesser stack memory, the bandwidth will decrease. Right? So, although this definition seems like it is not related to stack allocation, but stack allocation has direct effect on this bandwidth. So now, each application will have a bandwidth, required bandwidth. Required bandwidth means if I have the entire memory to myself, how fast can I compute? Right? So each thread, let's say thread T1, has a bandwidth required. So this is the required bandwidth for T1. Again, what does it mean? It means that if I have the entire memory to myself, I can execute on, I can give an output, or I can consume that BRW1 amount of data, I can operate on that amount of data and give an output in 1 second. That is what it means. Okay.
It has to give an output for implicitly considered payment. It is not that it just read through data in that much time.
Yeah. So that is a good point. That this is an average metric. This is an average metric. So a thread. So what happens is that if I give this required bandwidth to a thread, then you are assured that within 3 seconds it will respond. Now, within 3 seconds it will respond means it can respond in 0.3 seconds, it can respond in 30 milliseconds, or it can respond in 2.9 seconds. That is, this bandwidth does not say exactly when it will respond, but this says that if you give it this much bandwidth, then it will respond within 3 seconds. So exactly when it responds, you don't know. So because this is an average metric. This is an average metric. So for thread 1 you have this. Now let's say you have 10 threads. Now if you have 10 threads, then if you sum this bandwidth required, I over all I, then this might be much greater than the maximum bandwidth that can be allocated. Okay. Maximum bandwidth means you can think of the entire memory. Entire memory allocated per second might be maximum bandwidth. Right. Or the entire stack memory available. So entire memory minus code, minus data, minus heap. That much amount is memory available and you can give it to a thread every second. Right? So that is the maximum bandwidth, let's say. Now this summation might be more because you don't know there are multiple threads. Right? Now if this summation is more, you have to find a policy to give bandwidth to threads. So you cannot give required bandwidth to every thread. You cannot give that same bandwidth to every thread. Right? You have to give a little bit less amount. Now you can choose many different ways to give bandwidth to thread. You can say that okay, the first 10 or first 5 threads gets whatever is required, the next 5 doesn't get anything. Right? That is one way. But that is not the best way. Why? What do you mean by the best way? The one way that minimizes the average response time. Because that is the metric that we are after. We need to reduce response time. So we need a way that minimizes the average response time. Right? So what is that way? Turns out that this completely fair scheduler is a way to minimize average response time. So what is the completely fair scheduler? So if this is the case, if this happens, that summation of bandwidth is greater than the maximum bandwidth available, then what you do? So if the summation of the required bandwidths for our is greater than the maximum bandwidth available, then what you do is the allocated bandwidth of thread I. So this is the allocated bandwidth. Allocated bandwidth for thread I is calculated like this. Right? If you give this much allocated bandwidth, then it turns out that it minimizes the average response time. Now, this does not guarantee that if it minimizes average response time, it does not guarantee that all the threads will have response time less than 3 seconds. Right? Because this is less. Allocated bandwidth is less than what is required. So that doesn't guarantee that all threads will finish within 3 seconds. Right? So after this allocation, there might be cases that some threads take more than 3 seconds. So those threads will be killed. Right? But this is the best that you can do, a completely fair schedule. This is the best that you can do. You can minimize the average response time. Now it turns out that, like most kinds of optimal scheduling techniques, cannot be implemented in practice. Optimal scheduling techniques can never be implemented in practice. Now, why can't this be implemented in practice? Because of a very simple reason. If you want to do that, then basically you need to know all the processes that are executing in the system. Not only that, you also need to know all the future processes that are going to come. How do you know? There is no possibility. You cannot know. So in practice, you implement certain variants of this completely fair schedule. What variants? Maybe you have some windows, and you take 5 seconds, and within that, however many processes comes, I will give the bandwidth accordingly. Right? If a new process comes in, then I have to recompute this and reduce the bandwidth of all the processes. Right? So those kind of strategies you can take. So this is the completely fair scheduler which minimizes response time. Do you have any questions?
Number of threads will not change drastically in a given amount of time.
It can. You will be surprised. If in a general purpose computing system, it drastically changes. In smartphones, smartphones more so. Why? Because you have sensor interactions, right? New event occurs in a sensor, your background thread starts, right? So yes, it's a very dynamic environment. Threads get created, destroyed all the time.
Bandwidth is something which we can find only after the thread is completed.
No, each thread can request certain amount of bandwidth.
How do we
You don't know exactly how much they are executing, you don't really know. But that is what they can ask for, and BWIA is what is allocated, so you cannot use more than that.
but how do we know in advance how much?
You don't know. That's the problem, you just estimate. You have an estimation. You just assume, allocate this much. Right? You don't really know. So that's why, you just assume that, okay, let's say this is my record. So whoever is scheduling that thread, some operating system, background service is scheduling that thread, it says, okay, your required bandwidth is this much. You can do some analysis of code and say that from preliminary execution, I see that you require this much time, right? So which means that you can initially have a default bandwidth request at a very small amount, let's say. Now after executing, you saw that no, you would need more, so you increase that amount. So adaptively, you can find out what is the required bandwidth. But at the beginning, you don't really know.
If an app doesn't want to play fair, it can request like much larger bandwidth,
It won't get.
but it will still get more than what if it like.
Yes, yes, yes. Yeah, then it can stall other apps. Other apps are getting less memory and they are getting killed. Yeah, that can happen.
So like there is nothing to stop that.
No, there are mechanisms. There are mechanisms to stop that because this requested bandwidth a user program cannot ask. It is the purpose of the. It is the operating system that can only give you requested bandwidth. You can ask for it, but the operating system will decide how much to give you. So you cannot ask arbitrarily more.
Like let's say my program requires certain bandwidth B to perform like optimally, but I know that there will be many processes and I will be given less than. So I make a request of let's say 3B or something like that.
That is what I'm saying. That request is not up to you to decide. It is getting adaptively obtained by short runs of your process. So you write an application. What the operating system does, and this was very old technology. Nowadays, what it does, I don't know. So what it used to do was initially it will give you a small bandwidth request, regardless of what is your application. It does not matter. It gives you a very small requested bandwidth. Then it says you will run it, and it says that okay, even if I give you the entire requested amount, you are not being able to run. So let's increase it a little bit. So it's the operating system decides that, and it adaptively finds out the optimal bandwidth request. So you cannot choose. The operating system chooses for you.
If the OS chooses for me to back within what's the use of this?
So once the OS chooses a requested bandwidth, then is the function of the scheduler to decide whether I give you the requested bandwidth or not. So even if the OS chooses a requested bandwidth, it may not be able to give it to you.
OS choose wrongly.
Yes, the OS chose not wrongly. The OS chose said that okay, if I give you this, so if this process is given this amount of requested bandwidth, then it can definitely finish within 3 seconds. But then the real situation is that I cannot give. The CPU scheduler says that no, even if you request that much, I cannot give it. I can only give you A.
Previously, it was independent of other processes.
Which one?
Requested bandwidth.
Yes, it's still independent.
And now it's depending upon the allocated will be depending.
Yes,
on
allocated depends upon other processes.
that's why we won't be able to give that much allocation.
We won't be able to get one.
That much allocation.
Yes, yeah, it depends upon other processes. Yeah.
So, based on historical data, you record the bandwidth.
No, not historical data, based on the current data. So you give it a small amount initially, you don't talk about historical data, and you might use, but the operating system does not do it. You can choose to use historical data and find out, but it does not do it. So initially it just has a very small default value, regardless of what your program is. So if it has a very small default value, then most likely the operating system will give it to you. I mean, not the operating system, the scheduler. The scheduler will most likely allocate that small amount, right? So it allocates. If it sees that you have been allocated the requested amount and still you couldn't perform, the operating system will increase the requested amount. Then at some point it will so happen that it cannot give you the requested amount. It gives you the allocated amount, which is less than the requested amount. But you still perform, so that's fine.
But performance, does it like have a time limit like 2.9 seconds?
So 3 seconds, right? 3 seconds you didn't get killed.
They will get killed, so.
So if you get killed next time, you change the requested amount.
And you increase that by like linearly or?
Your choice. This is the choice of the operating system. Many different ways you can come up with. So there are different policies that you can take to increase, decrease, whatever you want. Any other questions? So we don't have anything, we don't have time to discuss anything. I thought we'll start with the thread coding, but we'll do that next class.